Hello. In this lecture, we're going to talk about measurement theory, and we will discuss some basic concepts about measurement theory. There are two basic things we have to understand. One of them is scale, the other one is measurement, the act of measurement itself. Actually, usually the act of measurement is described as assigning numbers to an object, to an event, or the properties associated with these things, numbers taken from a scale. You take these numbers from a scale and assigning them to an object or a property of an object. However, this scale is not just a simple collection of numbers. Scales have properties. So what kind of a scale you're using in a measurement actually describes what kind of measurement you're making. Okay? So there are four basic types of scales, and you can see them here. If we discuss them in detail, the first one is the nominal scale. Nominal scale is a naming scale. What it means is that it's the numbers in this scale is not much different than just tags or names. For example, if you ask a patient if he has pain or not, say a knee pain or not, the answer is yes or no. You can say if it says yes, it can be 1, and if it says no, it can be 0. But this is just a tag. 1 and 0 does not mean much. However, the nominal scale is the most primitive scale. However, it's probably one of the most used scales of the four, or one of the most popular scales, let's say. Many measurements are made using nominal scale in medicine and biology. The ordinal scale is a sorting scale. It sorts the quantity you're trying to, or the value of the quantity you're trying to measure. However, the difference between the numbers, the numbers that comes from the scale, does not represent equal difference between the value you're trying to measure. For example, the place the athletes get in a race is a good example. The first place, the second place, the third place. However, it doesn't mean that the performance difference between the performance of the athlete who takes the third place and the second place is the same with the athlete who takes the first place and the athlete takes the second place. The difference between the second place athlete and the third place athlete can be a few seconds, and the time they finish the race, they can be very close. However, the difference between these two and the first athlete, the athlete that took the first place, can be minutes, or it can be worse. It can be the difference between the first and second can be very close, but the difference between these two and the third can be very large. So the differences between these numbers is not fixed. They are just give you a sense of sorting. That's all it tells. So ordinal scale is a little bit more informative than a nominal scale. Then we come to the interval scale. Interval scale is a quantitative scale. We can say that the difference between the numbers are fixed, and they represent the same difference in the value you're trying to measure. For example, Fahrenheit and Celsius temperature scales are quantitative interval scales, which means that the difference between 10 degrees Celsius and 20 degrees Celsius is the same between the 100 degrees Celsius and 110 degrees Celsius. The quantity you're trying to measure, the temperature difference between these two couples, is exactly the same. However, as the 0 point is arbitrary, the 0 point does not mean the lack of or the absence of that property you're trying to measure. 0 degrees Celsius does not mean there is no temperature there. So it's an arbitrary 0 point. Because of this, the values, the temperature values you're trying to measure, or the ratio between these two, is not represented by the numbers that you're assigning to them. We'll come to this and explain this in detail in a few minutes. But let's keep this in mind. And the last one is the ratio scale. Ratio scale is a quantitative scale again. And the example for this is the Kelvin temperature scale. The Kelvin temperature scale, again, the differences between numbers is fixed. So the difference between 100 and 110 degrees Kelvin is the same with 2000 and 2010 degrees Kelvin. The temperature difference is the same. And also the ratios between these numbers that you assign is actually the real ratio between the quantities you're trying to measure, the value of the quantity you're trying to measure. Because the 0 point is not an arbitrary 0 point, it's a real natural 0 point, which means that at that point, if the temperature you're measuring is 0, there is no temperature there to measure. 0 means the absence of that value you're trying to measure. Natural 0 means that. Let's actually discuss this a little bit further. The Celsius temperature scale is an interval temperature scale. Okay. So the difference between minus 100 and minus 50 degrees Celsius is exactly the same between plus 50 and plus 100 degrees Celsius. The difference is 50 degrees of Celsius in both cases. And the temperature difference is the same. However, the 0 is arbitrary. 0 is does not mean that there's no temperature left at 0 degrees. The 0 degrees is chosen as the temperature that water freezes. So the ratio between, for example, 100 degrees Celsius and 50 degrees Celsius is 2. It doesn't mean that 100 degrees Celsius is 2 times more hot than the plus 50 degrees Celsius. Why? Because as the 0 point is arbitrary, I can bring it down to anywhere I like. So I can bring it down here and call this scale as Mehmet scale, degrees Mehmet. And now the numbers change. It's the same temperature. We are measuring the same 2 temperatures, but the numbers changed, so the ratio changed. So as you can see, the ratio between these numbers do not represent the ratio between the temperatures of those points. The differences are measure the difference between these 2 points correctly, but the ratio is not representing the ratio between the temperatures. So when you come to a ratio scale, when we come to the ratio scale is Kelvin, degrees Kelvin, as we discussed. The Kelvin temperature scale has a natural 0 point. Natural 0 point means that at 0 degrees Kelvin, there is no temperature left. So there is no minus Kelvin degrees Kelvin measurements. There's nothing below 0 Kelvin. Thus, the ratio between 200 Kelvin and 100 Kelvin degrees is exactly the ratio of the temperatures. So 200 Kelvin degrees Kelvin temperature is 2 times hotter or more hot than 100 degrees Kelvin. If the differences between the numbers you measure is the same, and then the temperature difference is the same. For example, the difference between 200 degrees Kelvin and 100 degrees Kelvin is exactly the difference between 1000 degrees Kelvin and 1100 degrees Kelvin. Difference is 100 degrees in both cases. Differences are the same. When we come to measurement itself, the act of measurement itself, there are 4 things we have to consider: calibration, sensitivity, dynamic range, accuracy and precision, and measurement error. Actually, the calibration means that if you use an interval ratio scale, you usually use an arbitrary unit, which means that the unit you're measuring with is unique to that measurement equipment or to the that experiment you're doing. It's unique to that instance. If you measure it with a different equipment or at a different time, at a different setup, you'll end up with different numbers. If you can match these 2 measurements, because you're measuring the same thing, and if you arrange things such that you'll end up with measuring the same numbers in these 2 cases, then you calibrated your measurements. That's what calibration is. So you're using a unit now which is fixed, like using a meter, or like using a gram, or using feet, or foot, or using pound, things like that. So you're using a fixed unit and compare your measurement to that unit. This is calibration. If you're not calibrated, sometimes you may not be able to calibrate your measurements. It's too difficult to calibrate. Then you use an arbitrary unit. And if you want to compare 2 different measurements, you have to be sure that that unit did not change. You may not know the corresponding regular or fixed unit corresponding to that measurement. However, you can compare your measurements because you're still using the same unit. If you cannot be sure that your unit did not change, then you cannot compare your measurements. The sensitivity and the dynamic range is sensitivity is the response that your system gives to a given quantity you're trying to measure. For example, if you have a scale to measure a weight of an object, as the weight of the object increases, the dial of the scale will shift. You add more weight, or you try to measure larger weight, then the shift will be larger. So it's called this graph shows the measured quantity versus the response of the measurement system. The sensitivity is the ratio between these 2 quantities. For example, you have a measurement system which has the property shown here. The A is one of the measurement system. So as you increase the measured quantity, the response increases. It doesn't have to be linear, but a preferable instrument responds linearly. And then you have a second measurement system shown with its property is shown, or the response property is shown with the red line. It's called B. This one has a larger or greater sensitivity than the system A, because it gives a larger response to the same quantity that you're trying to measure. So you can see that their responses to the same measured quantity is different, and B gives more response to the same measured quantity. However, you have to understand that they both give 0 response to a 0 quantity. This shift, if this shift is parallel, upwards or downwards, it does not change the sensitivity. It only changes the 0 point. You have to be careful about that. So, however, dynamic range means that window of measured quantity, the measurement system continue to respond to changes in the measured quantity. For example, here, after a certain point, the measurement system become unresponsive to the change in the measured quantity. So, actually, if you go beyond that point, you cannot measure the quantity you're trying to observe. Even if the measured quantity changes, you get a fixed response. This is called the measurement window, the dynamic range of the system. It's usually not linear, but the preferable systems have a linear range in between, in the middle of the window. So when you start to approach the ends of this window, you start to have a nonlinear response, and the curve starts to flatten, which means that it does not respond to the change in the measured quantity anymore. So you cannot measure those quantities. So this is dynamic range. When we come to accuracy, precision, and measurement error, now let's say that we use two different measurement systems, A and B. We are trying to measure the same quantity, shown by the red rectangle here. We're measuring the same thing. However, we repeat our measurements using the system A and using the system B, and we get different results. Okay? So this is measurement error. So the quantity does not change, but our measurements change, and these changes are arbitrary or random. However, as you can see, they are scattered around the point that you're trying to measure. And first of all, you have to understand that A has more scatter around the value you're trying to measure, or the quantity you're trying to measure. Is more scatter means it deviates more from the real value. Your measurements deviates more from the real value in A than it does in B. The B gives you more close results in each measurement. Every time you repeat the measurement, you end up with a similar result, similar measurement. So B has more precision than A. B is a precise measurement compared to A. However, they may be on average, or they can be gathered around a different point than the actual value you're trying to measure, as shown on the figure on the right hand side. A and B now is a little bit different. A is still scattered too much, so the precision is low. The B has less scatter, so you get more consistent measurements with B, the system B. However, the accuracy of B is worse than A, because the values you're trying to measure with B is gathered around a lower value than what actually you're trying to measure, as you can see here. So accuracy is the point, the average point, the measurement is scattered around. If it's closer to the value, actual value trying to measure, the accuracy is better. More scatter you have with consecutive measurements, you have slower precision. Okay, but a precise measurement may not be accurate. Okay. So what you can see is that the less precise measurement, the system A, you can make a less precise measurement because of the measurement errors. Each measurement is different because due to measurement errors. However, in the left-hand side, in both in A and B, the measurement errors are random. They are just the number of measurements you make above the real value or below the real value is more or less the same. However, on the right-hand side, the system B gives you consistently lower measurements. There's less scatter. However, the measurement error consistently gives you values below the actual value you're trying to measure. So there is a systematic error on top of random error in the system B. Okay, so if you're getting more and more accustomed to the terminology, there is another concept called resolution we have to understand. What's the resolution of the system? Resolution means how fine differences can you discriminate using this measurement system. Of course, sensitivity is related to resolution. For example, let's assume that you have two different measurement systems. One has the A is less sensitive than the system B. So you're measuring one quantity, say weight of something. So your scale will move this much for the same weight we are trying to measure. And you use the system B, so your scale, the measurement instrument scale will move more in a sensitive system or in a sensitive measurement system. So, which means that you can resolve finer details or finer differences using the system B clearly. However, in determining the resolution, the measurement error and precision is also important. For example, here, this time you're using the same system, but you're trying to measure two different values. A and B represent two different values for a quantity you're trying to measure, shown by the red triangles. B is a little bit lower than A. You're using the same system, and you have a measurement error, so you make repeated measurements of A, and using the same system, you're using repeated measurements of B. And as you can see, because of the measurement error, these two scattered measurements are almost close to each other. Say you take 2 points here, one you measured A, another point you measure B, even if the real value of A is larger than B, you can easily end up with some measurement smaller than in A than in B, as you can see, because there's a lot of scatter in your measurements. So you have to make many measurements and you average them and you do statistics about this. So this affects your resolution. If your precision is low, then your resolution is worse. If you do repeated measurements, you get consistent results, more consistent results, your precision is high, then you can resolve smaller differences in the value of the quantities you're trying to measure. Okay, so these concepts are intertwined, so you have to grasp an understanding, a complete understanding, or more global understanding of the subject. Otherwise, you can get easily confused. Go through this video once more, twice more, if you like, and try to understand everything we discussed here. These are important and basic concepts. See you in next lecture.